called a set. And a set is a collection of distinct objects. So distinct objects that are distinguishable from each other. So think of names. So, we can distinguish between Frank, Anne, Matthew, Christopher, Julia. These are distinct people. Okay. And you can do the same thing with numbers, objects, variables, and such a thing like that. And we denote a set using a new kind of notation. We call it set notation. And set notation involves using these curly brace brackets, okay, like this. And inside the curly brace brackets, you would put your set. And I'm just going to use a ... to show that we're going to have something inside that set. Okay. And we use n, okay, our set name, to denote how many, or the number of elements, or the number of objects in a set. Okay. Then I'm going to define the null set. So a null set is a set with no elements. Okay, so nothing inside. So we just use curly brace brackets. Let me see if I can draw them here. So here's a set of curly brace brackets, and I'm not putting anything inside. Let me just draw them nice. See if I can do them a little bit nicer. They're hard to draw, but with practice you get them. Okay, and if you don't like using curly brace brackets, another way to say null set is to draw this 0 with a line through it like that. Okay, so the word null, think of like if you ever took computer science, null, like a null memory, nothing in the memory. So null set. Okay, and a null set is a subset of every set. Oh, it's meaning it's a set that's inside other sets. Now this might sound like an abstract concept, but null sets have a usefulness just within mathematics, and it's like used later on when we study things like a intersection of two or more sets and things like that. But for now, it's just good enough that we have a definition. To give you a better picture of what a null set could look like, think of our classroom. Okay, so let's say the classroom is a set. We put curly brace brackets around our classroom, and inside our classroom we have these distinct objects, and these objects, I'll say, are the students. The students have different names. Okay, so let's say we have Israel, Daniel, to make up some other names. I don't know, Frank and John, and these are distinct students. But now imagine for a moment, there's a desk there that's empty. Okay. There's no student. That's an empty set. That's a null set. So a null set can exist inside our bigger set, which would be our classroom in this example, so that's just one way to illustrate what that null set is. Okay. Subset. So a set whose members are all members of another set. Okay, so all members of another set, so a subset. So think of it again, our classroom. What if you said, okay, we have one set of students who are grade 12s and another set of students that are grade 11s taking the same class. So the grade 12s would be a subset of my bigger set, which is the classroom, and then the grade 11s would be another subset of the bigger classroom set. Okay, so any set has 2 to the power of n subsets where n is the number of elements in the original set. Okay, and I'll illustrate this example of 2 to the power of n subsets in the next example. Okay, so let's look at this example. Example 1, consider a standard deck of 52 cards. Part A, how many elements are in the set for suits in the deck? So what are the suits in a deck of cards? Well, you have in the picture here diamonds, you have spades, you have hearts, and you have clubs. I'm just going to use these 4 letters to make it easier for us. Okay, so there are 4 elements or 4 suits in a deck. Okay, identify the suits using set notation. So our set, I'm going to say, is S. And the set is equal to, our set is going to be with these brace brackets, and the elements in our set are the hearts, H, clubs, C, spades, S, and diamonds, D. I'm going to close a set with the brace brackets again. Okay. How many possible subsets are in this set? Well, you have 2 to the power of n. How many is n? Well, n is 4 because I have 4 elements. So 2 to the power of 4. And 2 to the power of 4 is 16. So there are 16 possible subsets, including the null set. Okay, so let's identify all the possible subsets. So again, think of like this is the classroom. You have 4 of these students here, H, C, S, D. How many ways can you make them as subsets? So you can just have a subset of H. You can have a subset of each one by itself, right? So I'm going to put H, C, S, D. And this is going to be good practice to draw curly brace brackets if this is the first time in your life that you're doing them. And then you can have subsets where you have 2 of them. So HC, and we can have HD, and then we can have HS, and then you can have CD, and then you can have CS, and then you can have DS, and then you can have the ones with 3 of them inside. So HCD and HCS, and here the order doesn't matter. Here the order doesn't matter. So we're just listing the one combination, HDS, and then CDS, and then you have the one where you have all 4 of them as your set. So HCDS. So the whole entire set can be a subset within itself. And then you have the empty set. Okay, so here you have 4, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible subsets. Now, you don't actually use all of them like this. It depends on the kind of problem you're solving. Okay. Next definition, sample space. So the sample space is the set of all possible outcomes. Okay. So think of like, again, our classroom. So our classroom might be a set, but maybe the school could be an entire sample space because the school contains many, many more students, many more names. Okay, and our classroom is just a set of that sample space. And I'm going to denote this as S equals our bracket, and I'll put a dot dot dot. The sample space itself is a set, so you can use set notation. The event, the set of all outcomes that have a common characteristic. Okay, so this is going to be denoted A like we did before. And the complement, so the set of outcomes that are not included in an event is denoted A prime or tilde A. Okay, so what this means is if we have, let's say, 12 students in our classroom, and our classroom is a set of 12 student names, then the complement would be every other student name in our sample space. So if the other student, if our sample space was the school, then every other student would form the complement of our set, okay, or the complementary set. So A prime or tilde A. Okay, that's the best way I could think of at the moment to explain those kinds of definitions in the way maybe we can all understand. Okay, so example number 2: consider a single 6-sided die. Identify the sample space for rolling the die once. Okay, so you roll this die once. Then what's the possible outcomes you can get here? Well, you can get a 1, 2, 3, 4, 5, or a 6. Okay, and so if I'm using numbers, I'm just going to put commas to separate them. Yeah, I don't want you to think it's one big number, but it's individual 1-digit numbers. Okay. Part B, identify the number of outcomes for the event of rolling a number less than 5 and the subset that makes up the event. So my event, which I usually say is A, is going to be roll a number less than 5. Okay, so how many ways you can get a number less than 5? Well, you have 1, 2, 3, 4 ways. You're not including 5 because it's not less than or equal to, it's only less than. So it's only 4 possible outcomes. So the number of outcomes for our event is 4. Okay, so n is the number of outcomes, a is my event, and the number is 4. If I'm going to make subsets to show that event, so my subsets are going to be 1, 2, and 3, and 4. Okay. Part C, identify the number of outcomes for the complement of the event and the subset that makes up the event. So A prime is rolling not less than 5. Okay. I mean, logically, you would say, well, if it's not less than 5, it's going to be rolling a number greater than or equal to 5. So you only have, so n is the number of outcomes for the complement is just 2. You can either roll a 5 or you can roll a 6. So I'm going to write the subset notation for that. I can either roll a 5 here in curly brace brackets, or I can roll a 6. Okay. All right. So let's go down to our formula that we're going to use for theoretical probability. So theoretical probability is a probability based on the analysis of all possible outcomes. Now, we're not going to study huge kinds of probabilities because, this can get really crazy. We'll look at some smaller things and ones that we can easily measure the outcomes. And then later on, I'm going to show you ways that you can measure probability of bigger things using special counting techniques. Okay, so the probability formula we're going to use is P of A. So the probability of an event A is equal to N of A, so the number of ways that event can occur, divided by the number of outcomes in the sample space. Okay, so I want you to compare this formula to experimental probability. It looks the same, but they have slightly different meanings. Okay, so instead of dividing by the total number of trials, you're dividing by the total number of outcomes, the possible outcomes. Okay, probability of a complement event. So the probability that an event will not occur. That's what we mean by complementary. Okay, will not occur. So since an event and its complement together include all possible outcomes, then the sum of their probabilities is 1. Okay, so the sum of the probabilities of all the outcomes in your sample space are going to add up, or in your set are going to add up to 1. Okay, so the probability of A plus the probability of A prime is equal to 1. I'm just give you a little Venn diagram here. So here's a Venn diagram. If any of you don't know what that is, I'm just going to show you now. So here I'm just going to draw a box to represent my Venn diagram. So here we go. There's a box. And I'm going to just draw a circle. Inside my box, I'm going to have a circle. This circle represents the set of all the outcomes that I'm considering. So here, A, event A. All right. And then all the complementary events are going to be outside that set, and I denote that A prime. Okay, so I'm going to save that, and so there you go. The probability of all of A plus the probability of all of A prime gives you 1, which is the probability of all the outcomes in my sample space. Okay, we sometimes say S is my sample space. All right, and then you can rearrange the formula to find either a variable here. Keep in mind that this is all just notation. Okay, this is just notation. I'm not saying this is not P times A. No, it's not at all like that. It's just saying the probability of some input. My input is the event. Okay, and that's treated as a single number, single percentage, or a decimal. Example number 3. Using a standard deck of 52 cards, what is the probability of drawing an ace? So my event is drawing an ace. Okay, so the probability of drawing an ace is equal to the number of aces in the deck of 52 cards divided by the total number of cards. The number of cards is my sample space. The number of elements in my sample space is 52. Here, the number of objects in my set is 52. So I'm going to say here that if there are 4 aces in the deck, 4 divided by 52, and that's going to give me my probability. Let's reduce it in lowest terms. So or 1 over 13, or as a percentage, use your calculator for this one, 8%. So there's an 8% probability that I can draw an ace from a deck of cards. Okay, people who go gamble in the casino, they know these things. They know that the chance of getting an ace is going to be 8% if you have a deck of 52 cards. What about not drawing an ace for part B? So now we're looking for the complementary event. Any other outcome except drawing an ace. So P of A prime is 1 minus the probability of drawing an ace. So I'm going to do 1 minus 1 over 13. Okay, which is going to be, if you don't like fractions, we'll convert, you can use a calculator, but this is just 13 over 13 minus 1 over 13, and that's going to give me 12 over 13, okay? And 12 over 13 or you can say that is 92%. And the quick way of doing this is just to say, let's take the 8% over here, subtract it from 100, and you get 92%, okay? So it's a bigger probability to draw anything else but an ace. What about drawing a club? So if my event now, A is a club, I've got to know first how many clubs are there in a deck of cards. Okay, so I've given you decks of cards in class, you could count them, but I'll tell you here in this video that there are 13 cards. So n of A is equal to 13, and n of S is my 52 deck of cards. So I'm going to say here, n of A over n of S, so the probability of drawing a club is equal to 13 possible clubs from A1, ace 1, 2, 3, 4, 5, 6, ace 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king of clubs. And so 13 divided by 52 is going to be 3 over 52, okay, or 6%. If you change that into a percentage. What about drawing a red face card? So a red face card. How many red face cards are there? Well, there's a, let me just use a different color ink here. So there are red, there's a jack, there's a queen, and there's a king. These are the face cards, and you can get a red of, so there are two kinds. So you have the hearts, and you have the diamonds. So there are 6 possible red face cards, okay? 6 of them. So the probability of my event of getting a red face card is going to be 6 out of a deck of 52. Okay, and then if you reduce that in lowest terms, that's 3 out of 26. And if I take a calculator, I can calculate the probability as a percentage. And so 3 divided by 26 is 0.11 or 11%. So 11% chance. Okay, so there's other ways you can do probabilities. You can use tree diagrams. So tree diagrams are a way to help you organize possible outcomes for a combination of elements in an event. So what happens if you have repeating events here, or each choices in your outcomes? So let's go through a couple of examples like this. Okay, example number 4: Fiona has 2 shirts, blue and red, and 3 pairs of pants, green, white, and orange, that she can wear to her co-op placement. Suppose Fiona randomly picks a shirt and a pair of pants. Construct a tree diagram to identify the sample space for this probability experiment. So a tree diagram is very simple. You just start from a single point here, and then you just draw branches. So the first choice she's going to make is a choice on what color shirts she's going to wear. 1 second. Excuse me. Oh, okay. So she's going to make a blue shirt, or she can wear a red shirt. Let me just go back to the pen here. So, okay, blue shirt or a red shirt. Now, if Fiona chooses to do a blue shirt, okay, then what kind of pants can she pick? So she has 3 choices for the pants. So she's going to have a choice to pick a green pant, a white pant, or an orange pant. Okay, so what are the outcomes? Well, she can wear blue shirt, green pants, blue shirt, white pants, blue shirt, orange pants. Okay, what if she picked the red shirt? Well, she still has 3 outcomes for the pants. I'm going to draw 3 more branches connecting that. And so what are they? Well, again, green, white, and orange. So now if she picked a red shirt, the outcomes are red shirt, green pants, red shirt, white pants, red shirt, orange pants. So these, if you count all the ends of your branches, these are all the outcomes. Okay, so you have 6 outcomes. So therefore, the sample space is going to be all of these 6 outcomes. So blue green, blue white, blue orange, red green, red white, red orange. Okay, and you're perfectly okay to write your sets like this as shorthand letters. You know, you don't have to write the whole thing; it'll take you forever or a long time. I'm fine with just using letters. So we're going to say here the number of elements or the number of outcomes in our sample space is 6. So 6 outcomes. Okay. Part B. Fiona does not like to wear blue and green together, nor does she like orange and red together. What is the theoretical probability that she will randomly pick a shirt and pants combination that she does not like? So the event is something that she does not like. And so the probability of the event is equal to the number of ways that you can get that event to happen over the total number of possible outcomes. So how many outcomes will result in her not liking something? So she does not like to wear the blue and green together, and so he doesn't like to wear orange and red together. So why don't I look at my list here and look at the blue and green together? So there's blue and green, and there is orange and red. So where's orange and red? Down here. So there's 2 possible things that she does not like, 2 possible combinations. So I'm going to say here the probability of A is equal to 2 possible outcomes that she doesn't like out of 6, and which is 1 over 3, or you can say 33%. So therefore, Fiona has an approximately 33% chance of selecting a combo she does not like. Okay, all right. Let's go on to this activity. We're going to do this activity in class, but I do want to just go through it in the video in case you missed the activity in class. So we're going to use tables and charts as another way of organizing possible outcomes for a combination of elements in an event. So here's my next example. Use a chart to help you determine the following sum of 2 dice. We're going to add 2 numbers that we see on the dice. So what is the sum? Okay, so let's what happens if you roll the dice? So the first dice you get 1, 2, 3, 4, 5, 6. Second dice you get 1, 2, 3, 4, 5, 6. So if you add the possible combinations, if you roll double ones, you get a 2. 1 plus 2 here is 3. 1 plus 3 is 4. And as you can see, I'm just going to add 1 every single time. Okay, down here, 2 plus 1 is 3. 2 plus 2 is 4. And I'm just going to keep adding 1 down the row every single time to show my sums. And then 3 plus 1 is 4, 3 plus 2 is 5, 3 plus 3 is 6. So all I'm doing is adding row with the column number and the row number. So 3 plus 4 is 7, 3 plus 5 is 8, and 3 plus 6 is 9. Keep going. Down here, I'm just going to keep adding 1 every time as I go down the column. And just keep going down the column and keep adding 1. And you'll notice I can complete this table very simply, showing all the sums of all the possible combinations of rolling 2 dice. 8, 9, and 10, and 9, 10, 11, and 10, 11, and 12. Okay, so there's only one combination of dice that can give me 12. It's the double sixes. And then there's only one combination of dice that can give me 2, the double ones. All right, let's go down to our question. So what is the sum, part A? What is the sum or sums have the greatest theoretical probability? What is the value of this probability? So what's the sum that you can get most often? Well, it turns out the one you can get most often is the 7. Why? Because there are 6 ways to roll a 7. So I'm going to say here a sum of 7 is most common. Okay, so the probability of rolling a 7 is equal to the number of times you can get a 7, the number of possible outcomes you can get a 7, divided by the total number of possible outcomes. Okay, and that's going to be, well, there's 6 ways you can roll a 7. How many possible outcomes can you get rolling 2 dice? So all you have to do is count all the squares here in my table. So there are 6. It's a 6 by 6 grid. So that's 36. So 6 times 6 is 36. So there's 36 possible outcomes. If I reduce this fraction, it's just 1 over 6. Or as a percentage, in my calculator, I can do 1 divided by 6, and I'll get and multiply by 100, and I'll get 17%. Okay. Part B, what sum or sums, let me say, so 17% chance to get 7s. So lucky number 7. Part B, what sum or sums have the lowest probability? What is the value of this probability? Well, 2 and 12 occur the least. Okay, so the probability of getting a 2 is just 1 out of 36. And the probability of getting a 12 is just 1 out of 36. Okay, so that's the answer for that one. Very small chance. Part C, what is the probability of rolling a perfect square? Oh, what's a perfect square? You have to remember a little bit of mathematics. So perfect squares are a number that have a factor that if I square it, I get that original number. So I mean, I'm thinking about like the number 4. So 4 is just 2 squared, so 2 times 2 is 4. And then you have 9, so 3 times 3 is 9. Okay, no other numbers here are perfect squares. So it's just 4 and 9. So let's just do this here. So perfect squares are 4 and 9. The number of times you can get 4 is 3 times. The number of times you can roll a sum of 9 is 4 times. Just count the number of 4s on the table and count the number of 9s in the table. Okay, so the probability of getting a 4 or a 9, okay, that's my event. The successful outcomes are rolling a 4 or a 9. That's going to equal, well, if there are 3 possibilities to get 4 and 4 possibilities to get 9 together, that makes 7. And there are 36 possible outcomes. So my probability is 7 over 36. If I convert that to a percentage, it's going to be 19%. So there's a 19% chance of rolling a perfect square. So therefore, there is a 19% chance to roll a perfect square. Okay. Part D, what is the probability of not rolling a perfect square? So what I want is the complement. So P of A prime. Okay, we already know that P of A, the probability of rolling my events is 4 or 9, is equal to 19%. So P of A prime, if you follow the formula for the complement, it's going to be so 100% minus the probability of A. So 100 minus 19, which is 81%. Okay, so therefore there is a 81% chance of not rolling a perfect square. Okay, and that's our lesson for theoretical probability 1.2.